A user transfers $500 to a friend. Your API deducts $500 from their account. Right before you add the money to the friend's account, your back-end server crashes.
Section 1. The missing money problem. When that server crashes, the money is gone forever. Your customer is furious, and you're facing a massive financial compliance nightmare.
Why? Because you didn't build your database rights to be atomic. Today, we're covering the missing money problem, DynamoDB transactions, the two-phase commit trap, race conditions, cost and scaling limits, and the consistency illusion. Let me show you how to actually fix this and why even the fix can fail if you don't understand how it works under the hood.
Section 2. Enter DynamoDB transactions. To solve the missing money problem, you use Amazon DynamoDB transactions. Transactions provide atomicity, consistency, isolation, and durability, or ACID, in DynamoDB. But let's simplify that. It just means all or nothing. Amazon DynamoDB transactions simplify the developer experience of making coordinated all-or-nothing changes to multiple items, both within and across tables. With the TransactionWrite API, you can group multiple put, update, delete, and condition check actions. You submit these actions as a single TransactWriteItems operation that either completely succeeds or completely fails as a single unit. The exact same is true for multiple get actions, which you group and submit as a single TransactGetItems operation. Section 3. The two-phase commit trap. So you write the code, you group the deduction and the deposit, you deploy to production. You think you're safe. But suddenly, during a massive flash sale, your error logs light up with TransactionCanceledException. Your system is failing. Here is exactly what is happening and why transactions still fail. DynamoDB performs two underlying reads or writes of every item in the transaction, one to prepare the transaction and one to commit the transaction. Section 4. Handling race conditions. Think about that two-phase commit process for a second. It's a two-phase commit. DynamoDB locks the items, verifies that no other process is modifying them, and then writes the data. But what if user A and user B both click buy on the absolute last concert ticket at the exact same millisecond? This is a race condition. Both requests trigger a TransactWriteItems call. Both check the condition that the ticket is still available. One request wins the race and commits the change. The second request hits the prepare phase, realizes the item has been modified by the first request, and violently rejects the write, throwing a TransactionCanceledException. This is where optimistic locking comes in. Optimistic locking is a strategy to ensure that the client-side item that you're updating is exactly the same as the item currently in Amazon DynamoDB. It protects database rights from being overwritten by the rights of others and vice versa. But when a conflict happens, DynamoDB doesn't magically queue up the failed transaction and wait. It just fails. As an AWS developer, you must write custom logic in your application to catch that exception, reread the database to get the latest state, and decide if you should attempt the transaction again. And if you do try again, you must use exponential backoff. In addition to simple retries, all AWS SDKs use exponential backoff. Progressively longer waits will occur between retries for improved flow control. If you just hammer the database with instant retries, you'll cause a massive throttling cascade. Section 5. Cost and scaling limits. Now let's talk about these cost and scaling traps. This is heavily tested on the DVA-C02 exam. Because of that two-phase prepare and commit process, transactions cost double. Transactional write requests require 2 write capacity units, or WCUs, to perform 1 write per second for items up to 1 kilobyte. Transactional read requests require 2 read capacity units, or RCUs, to perform 1 read per second for items up to 4 kilobytes. If your table normally consumes 1,000 WCUs and you wrap all your code in transactions just to be safe, you instantly need 2,000 WCUs to do the exact same amount of work. Your latency goes up and your AWS bill doubles. Also, watch out for the physical limits. A single TransactWriteItems or TransactGetItems request has a hard limit of exactly 100 items. And the total payload cannot exceed 4 megabytes. I want to be clear, this information is a strict architectural constraint you must memorize. If you try to process an order with 101 items in the shopping cart, the API call will be rejected. You cannot use transactions for massive bulk data operations. Section 6. The consistency illusion. Now imagine this. Your transaction completely succeeds. the money is transferred. A Lambda function listening to DynamoDB streams wakes up to send an email receipt. DynamoDB streams captures a time-ordered sequence of item-level modifications in any DynamoDB table and stores this information in a log.
The Lambda function reads the stream, then queries a global secondary index to get the user's profile data to send the email. But the email goes to the wrong address. Why? Because even though the transaction was strongly consistent on the base table, global secondary indexes update asynchronously. The GSI is still eventually consistent. Your transaction succeeded, but the rest of your distributed system hasn't caught up yet.
Let's lock this down. 3 rapid takeaways. 1. TransactWriteItems provides ACID compliance and all-or-nothing execution, but costs exactly double the WCUs and RCUs due to the two-phase commit process. 2. Transactions will fail with a TransactionCanceledException during concurrent write conflicts, requiring you to implement optimistic locking and exponential backoff in your application code. 3. Transactions are strictly limited to 100 items and 4 megabytes per request, and while they guarantee consistency on the base table, downstream replicas and GSIs remain eventually consistent.
One final warning. Never use transactions as a default crunch. Only pay the double capacity cost and latency penalty when your business logic absolutely demands strict, multi-item atomicity. Look at your own code today. Are you building truly atomic systems, or are you just paying double for a false sense of security?